translated into gear wheels with awkward teeth counts like 53 and 127. How did the ancient engineers do this? Michael Wright had the simple answer.
There's nothing difficult about any number. 53 is no harder than 54. We think that the Greek mechanic started with a prepared sheet of metal. He didn't have a hacksaw, so he had to cut it out with a hammer and chisel. What I usually do for almost any number is to divide the wheel into 6 to begin with by stepping the radius round. Now, I ought to be fitting 8 and a large fraction into each of those 6 divisions. So now I'm going to attack it with a file and make teeth. That's 53 teeth. That's ready to go into my Antikythera mechanism. I suppose my Hellenistic workman friend would have taken about half an hour to make that.
Meanwhile, as Tony Freeth created his own digital model, he was suspicious of Wright's use of gear wheels with odd numbers like 53 teeth.
53 teeth. Why 53 teeth? It seemed to have no function. Odd prime number, no function. And I thought 54 was a much more likely number. You know, divisible by 2, divisible by 3 several times. So in my model, I changed Wright's 53 to 54. And it proved to be a huge mistake.
This tiny change would escalate into a major problem in the future. But there was a more pressing problem. None of the investigators working on the machine had ever been able to explain the function of the large wheel, the one with either 222 or 223 teeth at the back of the mechanism.
We were desperate for more data. We knew that the surfaces of many of the fragments were covered in inscriptions which were incredibly hard to read. And then I read about this technique invented by a guy called Tom Maltzbender at Hewlett-Packard. It was a brilliant technique for enhancing the surfaces, surface details. One of the ways this technique had been used is on paintings, for example, at the National Gallery in London, to look at the surfaces of paintings and just looking at brush strokes, the fingerprints, the essential form. And this can reveal things that are under the surface. Here, for example, is a painting by Frans Hals. And if I move the virtual light, I can see the brush strokes on the painting. I can see how the painter's applied all the brush strokes. And we thought this would be an absolutely brilliant technique to use on the Antikythera inscriptions. I got on very well with Tom, and I then set about persuading him to come to Athens to use his technique on the Antikythera mechanism. Tom had an absolutely brilliant insight, which is that you can look at a surface by taking a series of still photographs, 2D still photographs, with lighting from 50 different angles. Flashlights arranged in a dome, flash, and a picture's taken with the light at all these different angles. And this means that a computer can put all this information together, and it can take away all the confusions of the surface coloration and the surface texturing, and show you the essential form of the surface. This is beautiful. You can actually look in detail at an inscription, say, and the clarity of the image leaps out at you.
Both this technique and the X-rays proved invaluable in reading the inscriptions.
These inscriptions were very tiny, maximum a couple of millimeters high. I was working overnight in front of my computer and trying to transcribe what I was seeing. The letters appeared like ghosts within the fragments. Lambda, 230. Epsilon 235. Spiral sections 235. Should be the 19 years calendar. One particular night I've discovered a completely unknown layer of text. I tilted a little bit the angle and a whole new layer of inscription appeared. My heart was beating, and suddenly I started reading mechanical words about gears. The word gear appeared for the first time, like a kind of a user manual. This was totally unexpected.
And new data from the inscriptions was producing another significant breakthrough.
Sigma Kappa Gamma. It is there.
What is there? How much is there?
223.
223 is there?
Yes. The line below.